a medium, we're looking at refraction at a plane surface, and this medium is mu2 and this medium is mu1, and we have an object in this medium, let's say, and we have an observer in this medium who's viewing it normally. Then we saw that the position of the object appears to be something like this, where the apparent depth is equal to real depth divided by refractive index of medium 1 with respect to medium 2. This was the important thing. So in this case, I'm obviously assuming that mu1 is greater than mu2. That's why it's appearing to be at a lesser depth. This distance, pi, is equal to the actual depth PO divided by mu of 1 with respect to 2. So mu1 is greater than mu2, then pi will be less, like in my diagram. Otherwise, it will be more, that kind of situation. And then we also saw another application of this, where you have to apply this formula twice to understand refraction due to a slab. And that was both a very interesting and an important type of concept. So we have a refracting slab of thickness, let's say T, and its refractive index is mu2, whereas both sides of it we have mu1. So typically this mu1 is 1 only because it's air, but you can get a problem where it's water or something else. And again, you are having a situation where the line of sight is normal. So the observer is receiving the paraxial rays. So the object over here appears to be closer if mu2 is greater than mu1, which is generally the case. And this shift, this lateral shift we saw, it is simply derived as a formula. It is thickness into 1 minus 1 by mu. But again, what is the mu? It is thickness of refractive index of the medium of the slab with respect to the medium which is around the slab. So this was an important formula. Okay, so, and we had seen number of applications of these last time. So I'll just start with an example problem where we'll combine this with a mirror now. Okay, so we'll see this situation. So let's look at this example. So what we have this side is a concave mirror. Now this concave mirror has a radius of curvature of, let us say, 60 centimeters. Now we are also having a glass slab in front of it, like this. The refractive index of glass is 1.5, and the thickness of this slab, let us say, is 10 centimeters. Okay. Now also, from the pole of this lens, of this mirror to this slab, this distance is given to us as 40 centimeters. And now we are keeping a point object, like a point source of light, LED bulb or something like this. So it's X. This is a point source of light. So we want to find the value of X such that the reflected rays come back to the point source. That is, the final image coincides with object. It is at the position of the source. So we want to find that and make the ray diagram. To explain the situation. So let's start with this quickly, people. If you can work out this and tell me the answer, then immediately we'll move on to the next section. I'm just minimizing this so you can see the whole thing. Okay, so people, I'm hoping you understood what is happening in this equation. Like that question we discussed last time where we had the concave mirror with the liquid on top of it and all that. Any situation, remember, where your final image coincides with your original object, it has to result in the rays retracing their path. The rays literally have to come back from the path from which they started. So retracing always involves normal incidence at the mirror. So that is a hint for you. Any question which has this kind of situation, whatever the combination of lens and mirror or whatever it be, in this case it is slab and mirror, you have to understand that final image is at object. It always implies that the rays retrace their path. And rays retracing their path is only possible in one situation. That is when there is normal incidence at the mirror. Okay. So got a couple of answers, but I'm still looking for the correct answer. So just to give you an idea about ray diagram wise, what should happen here is that any paraxial rays which are incident from this, after this, it tend to bend a little towards the normal. And then again, it will emerge parallel to this. In terms of ray diagram, this is what should happen. This should be a normal incidence, so it should retrace its path. Retrace its path, and this will also retrace its path, and then this will also retrace its path. This is the situation that should happen. So now you have to solve for this situation numerically. I'll give you a hint with the ray diagram. Now you have to just solve this numerically. No, I'm still looking for the correct answer. You see, the answer actually lies in the ray diagram. Okay, now what we want in this ray diagram is that First of all, let's draw a sort of principal axis. This is where our pole is. Now, if this is 40 centimeters and this is 10 centimeters, so 50, the center of curvature of the lens of the mirror is somewhere here. Now, this ray should be what? It should be normal incidence. That means it should be coming from where? It should be coming from the center of curvature. So, this thing should be the center of curvature. Right. So, when you produce back the incident ray on the mirror, it should appear to be coming from the center of curvature of the mirror. So, that means this distance here, from here to here, this should be 60 centimeters. That is the radius of the mirror. Now, this refraction that is happening through the slab. So, this shift from here to here is how much? It is a lateral shift because of the slab. This is the delta x. So all you have to do is now apply that formula. So delta x is thickness into 1 minus 1 by mu. So it is 10 centimeters into 1 minus 2 by 3. So it is 10 by 3 or approximately 3.33 centimeters. So that's your delta x. So now we wanted to find out this distance, how much this is. So here you can see this distance itself will be 10 because this is 50. So you can see x will become how much? X will become 10 plus 3.3. So you can take it like this. X will be 60 minus of 40 plus 10 plus delta x. So it will be 13.3 centimeters approximately. So that principle of reversibility of light and retracing the path, yes, Ayush, good, that's correct. Is an extremely important type of concept while you're solving these type of questions. Okay, now just a word about your upcoming test on Saturday or Sunday, whatever next. The portion in optics will be up to lenses. Okay? It's written geometrical optics, but it will be part of geometrical optics. So it will be only up to today's lecture where we'll cover thin lenses. After this, we'll be discussing few more things like thin prisms, and then optical instruments, and also something called aberrations. So those things all will not be part of the upcoming test. The test will be about spherical mirrors, thin lenses, refraction at spherical surface, and of course plane mirrors are there from before. So everything we've discussed till today's lecture, including today's lecture. Okay, so I think this should be clear by now. Okay, I have the confirmation from most people. So let's move on to the next section we'll discuss now. So before we move on to refraction at spherical surface, we will quickly look at a concept called this thing, critical angle and total internal reflection. Let us understand this one. So as you know, if light is refracting from a denser medium into a rarer medium, it tends to bend away from the normal. Just for example, suppose you have some medium like glass, outside there is air. So let's say this is mu2 and this is mu1. Now if we have an incidence at a point like this, where this is the normal. So if the ray is going from glass into air or from the denser medium into the rarer medium, then that kind of ray will always tend to bend away from the normal. So you have a situation like this, that tends to be like this. Okay. So this is the angle of incidence, because that's the direction in which refraction is happening. You can see that mu2 sin I is equal to mu1 sin R, and mu2 is greater than mu1. So automatically what happens is I becomes less than R becomes greater. Okay. So now at some stage, if we increase the angle of incidence, what will happen is the angle of refraction will also tend to increase. So as we increase the angle of incidence, this is what tends to happen to the angle of refraction. That tends to increase further, go from this to this. So we can reach a certain critical stage where then what happens is that this angle of refraction in fact becomes 90 degrees. So the ray that is coming out is literally not coming out, it is just tangential to the surface of refraction. It's what we call the grazing emergence. It comes out grazing the surface of, if it's a glass slab, the ray actually doesn't come out into air. It just grazes the surface of the glass slab. So when that happens, we say the angle of incidence is called the critical angle. Okay, so that is first of all the concept of critical angle, and we'll develop a formula for it. So there's a particular angle, and that angle is coming, the formula for that angle will come from refractive index, the value of that angle. There's a particular angle of incidence for which this is what it is. The ray that is going to emerge out is going to come out almost at perpendicular. The angle of refraction will become like this. So when that happens, the angle of incidence involved, that is called the critical angle, denoted by the symbol IC. So critical angle such that for incidence at that critical angle, the refracted angle becomes 90 degrees, or what we say is we have what is called a grazing emergence. So this ray which is coming out, this is called, it grazes the surface or comes out tangentially. It's a grazing emergent ray. Now in terms of formula, you will see apply Snell's law. So mu2 sine of critical angle becomes mu1 into sine of 90 degrees. And that is, so the formula of critical angle now becomes that it is sine inverse of mu1 by mu2. Or the better way to remember the working formula is this, that the critical angle is given by the formula for that pair of medium. It is sine inverse of 1 upon mu of 2 with respect to 1. So this is the formula of critical angle for a pair of medium of refractive index mu2 greater than mu1. So this is firstly the definition of critical angle, and you need to understand it. But before that, you need to understand the process, okay, that when light is going from denser to rarer, it bends away from the normal. And the more you bend the incident ray at a larger angle of incidence, the more the refracted ray also bends. So at a particular value of angle of incidence, the refracted ray just comes out, just grazing the surface, or the angle of refraction just about becomes 90 degrees. So that particular angle at which this happens, that Okay, so this is about critical angle, people. Now, next thing we'll see is total internal reflection. So that is what happens when angle of incidence is greater than critical angle for refraction from denser to rarer medium. This is my mu 2, this is my mu 1. But now at the point of incidence, if my angle of incidence is so large that it's more than the critical angle, which is given by that formula, sine inverse 1 by mu of 2 with respect to 1. Then instead of refracting into the denser, into the rarer medium, the ray just reflects now. So this angle of reflection now becomes equal to this angle of incidence. This angle and this angle are the same. So for I greater than critical angle, or I greater than sine inverse 1 by mu of 2 with respect to 1, total internal reflection happens such that angle of reflection is equal to angle of incidence. It follows the law of reflection. Okay, so just make a note of this and we'll just work out an example or two of this. Understand? Okay, so let's look at this with an example. Suppose we have a triangular glass prism like this. And we have a ray of light which is incident on this surface normally like this. This angle is 90 degrees. And suppose for my prism, this angle is theta. We want to trace the ray diagram. Theta is given to me as, suppose, 30 degrees. If the refractive index of glass is suppose 2.4 in one case. Another case, the refractive index of glass, let us say 1.73. Both the cases. So just try this out. So trace the ray diagram and find the final deviation. Finally, how much the ray deviates from the initial position. Angular deviation. Okay, so anybody got the answer in the first part? See, what will happen here is this first event, it will go undeviated. So it's incident like this because it's a normal incidence. Plane surface पे angle of incidence 0 है, the angle of refraction will be 0. Now draw the normal at this surface. So that normal is, let's say, a line like this. So the angle of incidence here is how much? It's theta only. Whatever that theta is, that angle of incidence is that much. Because you can see this is 90 minus theta. So angle of incidence is equal to theta. So in the first case, you can see that angle of incidence, which is theta, is 30 degrees, is greater than critical angle. Because in the first case, mu of glass is 2.4. So sine of critical angle is 1 upon 2.4. Okay. So that is 5 by 12. And sine of I is sine 30 degrees, which is 1 by 2. Okay. Or that is 6 by 12. So I is greater than critical angle. So what happens over there is total internal reflection happens. This is what happens in the first case. So TIR happens now means that this ray after refraction, I mean, it will now reflect. It will go off like this. Or something like this. Where this angle is also theta. Okay. And then it will be incident over here. where we can now find the new angle of incidence, which will be this angle. Okay. So you can see that that angle of incidence will also become 30 actually. But in a more proper ray diagram, it would be something like this. That 30-60 triangle would probably look something like this. So now this incident ray comes here and it deviates something like this. The normal at this point is like this. So this is 30 degrees because this is 30 degrees. And then this is 30 degrees. So this whole thing is 60 degrees. Okay. So therefore, at the second place, the angle is making with the normal will again become 30 degrees. Something like this. So again, you can see the del B TIR, total internal reflection. So again, this is 30 degrees. So again, this will reflect like this. Come back here. So we'll have to have this kind of. Okay. So this angle is also 30. So this is 60, this is 60. So now again, this angle is 60. Okay. So this time, this is the normal. So it will keep going on this kind of path. So now this angle is 60. Okay. So the first, second, and third, they're all total internal reflections. Okay. Now let's see what's happening in the fourth one over here. So this angle is 30. So this angle is how much? 120. So this angle is 60. So again, this angle is 30. So it has this strange kind of path. So there are multiple reflections that keep happening. Okay. Multiple TIRs that happen in this case. So all of you are following this first case. This what's happening. Now to illustrate the second case, you're taking the refractive index of glass as just √3. It is approximately √3. So this problem that we are studying, this is not officially what we call the prism analysis. In prism analysis, there's a lot more things that we do, like angle of minimum deviation and things like that, and that will come towards the end after we complete lenses. Okay, this is just a general application of Snell's law and total internal reflection in this case. TIR and critical angle is like a special case of application of Snell's law. Okay. Critical angle is that special case where angle of refraction becomes 90, and TIR is that special case where I is more than critical angle. So okay, so second case, let's look into it now. So nothing changes for the first event because it's a normal incidence. So it's nothing to do with the refractive index. The beam of light which is incident normally at this plane surface, it just go undeviated, nothing happens to it. That's why geometrically it's the same thing now over here. But only now you will see that the angle of incidence is equal to this angle theta, because this is normal. So I is equal to theta is equal to 30 degrees. Whereas this time refractive index of glass is 1.73. So critical angle is sine inverse of 1 by 1.73. So it's approximately, you can say that sine of critical angle is 1 by root 3 or root 3 by 3. Okay. Whereas sine of I is half, that is 0.5, and this is approximately how much? 1.73 divided by 3, so that is 6 to something. Okay, so you can see from this and this that the angle of incidence is less than critical angle. So there is refraction. There's no total internal reflection. Okay. So this time what happens now is that it bends away from the normal, but it bends into air. So something like this. This is what happens after this. And let's say this angle is the angle of refraction. So refractive index of glass into sine I is equal to air, which is 1 into sine R. So you can say root 3 times sine 30 degrees is equal to sine R, and that will give you R as 60 degrees. Now once you got R as 60 degrees, now in this question it makes sense to understand what is the deviation. So pay attention here, I'll explain to you. Deviation is this, that if the incident ray had not got bent, it would have gone on this path. Now it has got bent like this. So this angle is called the angular deviation. Okay. So the angular deviation delta over here is actually R minus I, which in this case is also 30 degrees. So this is how you solve the second part. Okay, people. So that's about these type of questions. Now we come to the very major next portion of optics for us, which will eventually include lenses. But first, we'll understand. So this is a very critical next phase we're looking at. So refraction at a spherical surface. Okay, so this is this kind of situation. Suppose we have a solid sphere of glass and we have a beam of light. This is incident something like this. So after refraction, it might become something like this. And again, after refraction, it might become something like this. So these are two instances where we can see that there is refraction happening at spherical surface. So, if this is the angle of incidence, it will tend to bend towards the normal because it's going from air to glass. Then for the second one, if this is the angle of incidence, it will tend to bend away from the normal. So the angle of refraction, let's say R prime, will become like this. It is I prime. So these are, general cases. Now, specifically what we want to do is, we want to understand a formula for a point object's image due to refraction from a single surface. So point object's image due to refraction at a spherical surface. Okay. And again, this is from the normal line of sight. That means we will be considering only paraxial rays. Let's look at that kind of situation. Okay. So for example, we have this situation now. We have this is glass. So refractive index is mu g. And this is a convex surface of glass. And let's say this surface is center of curvature lies somewhere over here. So this is a spherical surface. So it has a center of curvature, and that center of curvature, let's say, lies over here. Okay. And the radius of this glass surface is R. So this point is a so-called pole. Now we have kept something like a point source of light here as the object, like a point object. We want to find out what happens to the paraxial rays. So it is basically like a version of spherical mirrors, but there we are applying laws of reflection. Here we will be applying laws of refraction. That's the only difference. Okay. So consider an incident ray like this. In fact, let's call this O only. So that you can use the same nomenclature. So consider OQ as a ray for which alpha is actually very small. So it becomes a paraxial ray. So if alpha is a small angle, then O cube becomes a paraxial. Just a moment, I have somebody in the waiting room. Okay. So this is a paraxial incident ray. That kind of situation. Okay. So now you can see that at this point, our normal would be this line. A normal would be this line, and the angle of incidence would therefore be this angle with respect to the dotted line with this PQ. Okay, so this here would become the angle of incidence. Okay. Now assume that obviously glass is denser, and this side we have air. So its refractive index is mu A. So refractive index of glass is more than the refractive index of air. So it tends to bend towards the normal. So instead of going like this, it bends a little bit like this, let's say. Oops. From this point, it bends a little bit like this, such that now this becomes the angle of refraction. Okay, so that becomes the angle of refraction such that, okay, Snell's law I'll write later, but first let's understand where the image would be over here in this diagram. Okay. So to understand the image, let me now say that I produce this ray back and it meets somewhere over here. Okay, so when I produce this refracted ray backwards, let's say it meets the principal axis somewhere here. So it meets the principal axis somewhere here. Okay. Now in this diagram, again as usual, we will take this angle as beta, okay, and we will take this angle here, this one, as gamma, and we'll develop that same kind of relation like we've done in the past for alpha, beta, gamma, which will give us the relationship between the object distance OP, the image distance IP, and the radius of curvature CP. But the only difference is previously we've done that for reflection where I was equal to R. Now we are doing it for refraction. So Snell's law, that thing applied over here, will be mu of air into sine I is equal to mu of glass into sine R. Okay. Now since alpha is small, because we are considering only paraxial waves, so I and R are also small angles. So sine I is approximately I. Sine R is approximately R. So Snell's law gets modified a little into refractive index of A into I is equal to refractive index of glass into R. So this becomes my first equation. The relationship between I and R, which in reflection was I is equal to R, here it becomes according to the ratio of refractive indexes. Okay. Now next what we have to do is we have to substitute I and R in terms of alpha, beta and gamma. And then we can relate alpha, beta and gamma with the distances. So we'll get the relationship between the object distance and the image distance. Okay. So to relate with alpha, beta and gamma, now again let's concentrate on this triangle and see how we can do that. So I have one choice of triangle as this one, OCQ. So if you see the triangle OCQ, for that I is the exterior angle. Now this is the exterior angle, and alpha and beta are the interior opposite angles. So alpha plus beta will become equal to I. Okay. And similarly, if you see the other triangle ICQ, that is this ray only produced back. Okay, so uske liye kya ho raha hai? R is the exterior angle and R is the sum of what? Gamma and beta. Okay, so that's what we'll do over here. So I'm just zooming out of this a little and writing that over here. So now you consider triangle OCQ. Okay, so just follow this triangle, the one made by the incident ray OQ and the normal CQ, and the exterior angle is I. So the exterior angle I is becoming the sum of the interior opposites. So that's alpha plus beta. That's my second equation. Okay. And now similarly consider the triangle formed by this one IC, the normal CQ, and the refracted ray produced back, which is IQ. Okay. So triangle ICQ. So in that, what is happening? The angle of refraction R is the exterior angle, and that is becoming the sum of gamma plus beta. Okay, people, is this clear? See, in that triangle, it's like this. This is C. And this angle only is R. That is the sum of gamma plus beta. Whereas in the other triangle OCQ, it was like this. Alright. So understood now how this is working out. Okay, so this becomes my third equation. So now just substitute these two in the first equation. So this equation becomes refractive index of air into I, which is alpha plus beta, is equal to refractive index of glass into R, which is gamma plus. Okay. So keep the term of beta on one side and the other terms on this side. So air ka refractive index into alpha. Division will come later. So refractive index of air into alpha minus refractive index of glass into gamma is equal to refractive index of glass minus refractive index of air into beta. This is what we do. Okay. Now replace alpha with approximately arc length PQ divided by object distance. Replace beta with exactly arc length PQ divided by CP, the radius of curvature, and gamma again approximately arc length PQ divided by image distance IP. This is all coming from small angle approximation. So now put that over there and you get the formula refractive index of air upon OP minus refractive index of glass upon PI is equal to glass minus air divided by EC. So this is the relationship that we are getting between the object distance, the image distance, and the radius of the spherical surface, the radius of curvature. Of course, we will take this one step further with the Cartesian sign convention, but first make sure you understand all the steps here. Okay, people, so this is clear. Now, next thing we'll do is we'll incorporate Cartesian sign convention in this and generalize this. So, with Cartesian sign convention, this case actually becomes like this. Suppose this medium is mu2. I'm generalizing it further. This medium is mu1. In this case, this is of course air and that is glass. So pole over here, center of curvature on this side, and we had kept the object somewhere here. So what we saw is that an incident ray like this bent towards the normal, went something like this, such that when we produce this ray back, give us an image somewhere here. So one thing, let's remove this one and let's produce forward this one. Okay. Next up, see that this is the refracted ray produced back. So this becomes my like a virtual image at this point because it's not somewhere where the real rays. And in this whole diagram, of course, the normal is this. Anyway, so this point was our Q. This was our angle of incidence, this whole angle. Whereas this was our angle of refraction. And we had labeled these angles as usual as alpha, this one as gamma, this one is beta. And doing all that analysis, we had seen, you would see, we had got the relationship that refractive index of glass so refractive index of air divided by PO minus refractive index of glass divided by PI was equal to glass minus air refractive index divided by PC. Now next what we'll do is incorporate Cartesian sign convention. So in that Cartesian sign convention, this side will become a positive quantity, this side of the pole will become a negative quantity. So we'll have to substitute with sign convention, we'll have to substitute U as minus PU, V as minus PI, whereas R will be plus of PC. So in other words, in the above thing, we'll substitute that, and from that we'll get the generic formula. Just a second. Software is okay. So we'll get the generic formula that substitute this, this will become minus V, this will become minus U. So this will become refractive index of 2 by V minus refractive index of 1 by U is equal to mu2 minus mu1 by R, because we'll also substitute refractive index of glass as mu2 and refractive index of air as mu1 because it is from air to glass. Okay. In other words, it is from medium 1, which has a refractive index mu1, to medium 2, which has a refractive index mu2. So for this reference and with a Cartesian sign convention, our final formula becomes this. So this is the generic formula that we'll apply every time there is refraction at a spherical surface. So I'm showing you the derivation for one case, which is a convex surface for rays going from rarer to denser. But like that, there can be concave surface for denser to rarer, there can be concave from rarer to denser, and there can be convex from denser to rarer. So in all, there can be 4 cases, 2 types of surfaces and 2 types of pairs of media, denser to rarer or rarer to denser. So in each one, if you do the similar kind of derivation, this formula will come out to be different. The POPI, the distance formula will come out to be different. But with sign convention, this formula will always come out to be the same. So this is the general formula. Okay. With the signs, okay, and it applies to all cases of refraction at a spherical surface. So this in itself becomes an application level formula where we use it for certain types of questions. And of course, apart from this, this will also be used to derive the focal length of a thin lens. So what is happening is a thin lens is an optical medium like glass or plastic or whatever, transparent optical medium, which is bounded by 2 spherical surfaces. So this same phenomena which we studied here, refraction at a spherical surface, is happening back to back twice as light goes to a lens. So it is ultimately application of this formula only, which will give us what is called lens maker's formula, which tells us how to calculate the focal length of a given lens. Okay, so this same kind of derivation you can repeat for a whole set of situations like this, not just this one. So for example, you can have other cases where something like this is happening. There is refraction at a concave surface. Glass in this side is air. So I'm just giving you a brief idea of the ray diagram. Then you work out the situation yourself and you'll understand how this happens. So here a ray of light incident like this, suppose, and suppose the center of curvature is somewhere here. This is your normal. So this will tend to bend towards the normal. So something like this will happen now. It will bend towards the normal. So when you produce this back, it will give you an image somewhere here. So this is one case. Okay. Then similarly, you could have a case where you have a convex surface, the denser and with a could have a reverse of this. What we discussed just now, we could have reverse of that. We have water over here and air on this side. The center of curvature is here. But the object is actually inside water. Like this. So here an incident ray like this, it will tend to bend away from the normal instead of towards the normal. As it tends to bend away from the normal, and to go like this now. So you could get an image over here. So all these cases, you take that alpha, beta, gamma method and first calculate the relationship between OP, PI and PC, but then put the sign convention. So with sign convention, every time you will see, you will get the same formula, that the generic formula, that mu2 by V minus mu1 by U, that formula. This one. Just a moment, people. I'll just refresh the whiteboard software. Right. So next up, let's look at an application example. In this example, what is happening is we have a solid spherical glass body kind of thing. It's like a glass ball. So this is a solid sphere made of glass, which has refractive index 3/2. Okay. And the radius, let us say 60 centimeters. Okay. Now inside that solid sphere, let's say we have something like a dust particle or just some kind of a air bubble or particle like this, which is over here. And we have two observers. One is the observer A and the observer B, who are both viewing it normally but from opposite ends. These are just two diameters arbitrarily drawn. So this is the center of curvature, and the distance PC is given to us as, suppose, 20 centimeters. So find the position of the point object or the particle as seen by observer A and as seen by observer B with respect to the surface of the sphere. Okay. So according to this observer, it will be at a certain depth behind this surface. According to this observer, it will be at a certain depth behind this surface. But for that, we can't use the real depth apparent depth formula, because what's happening here, the refraction of rays is not happening at a plane surface, it is happening at a spherical surface. So we'll have to use that spherical formula, and from that we'll have to determine. Okay. So just try out this question. So according to this guy A, it is so many centimeters behind this surface, and according to B, it is so many centimeters behind this surface. Now in reality, for A, it is the point is at an actual depth of 40 centimeters, and for this guy, so students, I'm just having an internet outage. Just need to go and check my connection. Okay. So hope you are getting the whiteboard. In the meantime, I will just connect. I'll reconnect and check my connection. See what's happening. Okay. So hope you are able to. You are receiving the whiteboard and you can solve the problem using